All right, this actually is going to work this time. You're laughing. And autofocus. This is Aerospace Engineering and AP Physics C, for that matter, Orbital Mechanics, Homework 7, Circular, Elliptical, and Hoffman Orbits. The answer key. Number 1, a satellite orbits the Earth at a constant altitude of 428 kilometers above its surface. Calculate the orbital period of the satellite and express your final answer in units of minutes. Well, of course, to get the orbital radius, you're going to have to take the radius of the Earth and add to that the orbital altitude of the satellite above the surface of the Earth. You know the mass of the Earth is 5.974 times 10 to the 24th power kilograms, and you know the universal gravitational constant, G, is equal to 6.672 times 10 to the negative 11th power newtons meters squared per kilogram squared, and therefore, to find the orbital period, you would use Newton's version of Kepler's third law. T squared equals 4 pi squared r cubed over gm. And of course, I just wrote a program to do this for me. So I'm going to just run my dumb program, which is not called dumb program, but it's called program 0. Central body is Earth. And this is going to be a circular orbit with a altitude given of 428 kilometers. 428, enter. There's the answer key. The orbital period is 93 minutes. Ta-da! Or if you like, it's 5,588 seconds, but in minutes, that's 93. Now, what I could do is actually quit this and go, what is 5,588 divided by 60? And it says 93.1 minutes. Ta-da! So there is the answer to number 1. Number 2, a second satellite also orbits the Earth. This second satellite is moving at an orbital speed of 2,120 meters per second in the circular orbit. To calculate the orbital radius, I don't have a program for that one. So V squared equals gm over r, and I need to solve for r. So r equals gm over v squared, and the orbital radius will be in units of meters when I get done. This is going to be alpha g alpha m, mass of the Earth, divided by 2120 squared, enter, is a whole bunch of meters. Divide that by 1,000, and I have an orbital radius of 88,600, call it 80 kilometers. And even that is with, well, one more sig figs than I should have. Okay, I'm going to pause this video. All right, so for problem 3, an Orion spaceship is in an elliptical orbit around the moon. If the Orion spacecraft is at a periapsis altitude of 70.0 kilometers above the surface of the moon and an apoapsis altitude of 425 kilometers above the surface, then calculate part A, part B, part C, part D. All right, so for each one of these, you need to recognize that when you are looking at the moon and you have an periapsis altitude, h, that the periapsis radius is the radius of the moon plus the altitude above the surface of the moon. And the apoapsis radius is the radius of the moon plus the apoapsis altitude above the surface of the moon. Peri means nearest, apo means farthest. So closest point in the elliptical orbit, farthest point in the elliptical orbit. To get the semi-major axis, A is going to be the average of those two orbit radii. So peri plus apo over 2. Orbital period will be from Newton's version of Kepler's third law. T squared equals 4 pi squared a cubed over gm. Part C will be the average orbital velocity, which we have to calculate, times the square root of the apoapsis radius over the periapsis radius. Part D will be the average orbital velocity of the elliptical transfer orbit times the square root of the periapsis radius over the apoapsis radius. Great. I have a program that's going to do all of it for me. So let's just turn my calculator on and fire up the program orbit. I'm going to choose my central body to be the moon. I'm going to choose to even zoom in a little bit so you can see the answers coming along. All right, so this is going to be an elliptical orbit. Boop. And I'm going to put in 2 radii. For the first radii, it is the radius of the moon, whatever that is, plus 70 kilometers. For the second radius, it's the radius of the moon, which I just store whatever that is as b in my calculator, plus 425 kilometers. Boop. So here's all the answers. The semi-major axis, part A is 1,986 kilometers. Because I like expressing it in kilometers, not meters. The orbital period, T, is 7,939 seconds. The periapsis velocity is 1,719 meters per second. And the apoapsis velocity is 1,437 meters per second. Whoops, I don't really want to quit. Of course, if you write a program, you need to take the trouble to debug the program, debug the program, debug the program over and over and over until you're pretty confident that it's probably right, but always be a little skeptical about it anyways. These numbers look reasonable. I can show you examples of unreasonable numbers, but that's a different story. All right, a question came up on how did I calculate the average orbital velocity for the elliptical orbit? And the answer is I used v is equal to the square root of g times m divided by the semi-major axis A. And of course, when you do this, you have to use the mass of the moon, not the mass of the Earth. And you have to convert the semi-major axis into meters and be careful that you don't put them in as kilometers. So whatever the mass of the moon is, something times, I think, 10 to the 22nd power. Actually, I could just look it up right now. Oh, what is the mass of the moon? And it says 7.348 times 10 to the 22nd power kilograms. The radius of the moon is 1,738 kilometers. The semi-major axis is 1,986 kilometers. So when you go square root of g times the mass of the moon divided by 1,986,000 meters, you get an average orbital speed of 1,571 meters per second. I didn't ask for that, but that is the number that I needed to have to calculate part C and part D. Okay, problem 4. A Dragon spacecraft is in a circular orbit around the Earth. Its orbital period is 3.20 hours. The crew decides to undergo a hop and transfer to a circular orbit with a period of 4.80 hours. Calculate part A, B, Okay, well, goodness. For the inner orbital velocity, that's going to be the period first will have to be converted to orbital radius. So you'll first have to use t squared equals 4 pi squared r cubed over gm and rearrange and solve for r. And after you solve for r, then v equals the square root of gm over r to answer part A. Then do the same process for part B. To get part C, you first need to calculate the semi-major axis, which is the average of the perigee radius and the apogee radius. So r peri plus r apo divided by 2. And once you have that value, then you could calculate the average speed using square root of gm over r. To get the transfer orbit periapsis velocity, it's the same as in problem 3. Part E is the same as problem 3, part D. The delta V's will be basically your answer from part D minus your answer from part A. For part G, your answer from part B minus your answer to part E. Part H is your answer from F plus your answer from G. And for the time of flight, we didn't calculate it yet, but first t squared equals 4 pi squared a cubed over gm, and then take that period for the elliptical orbit and divide it in half. Fortunately, I have a program that does this. I'm so happy to have a program that does this. I'm going to run my program. My central body shall be the Earth. And I don't think I can put, I'm not sure how I can put in the information. So let me try a Hoffman transfer. And nope, I need to calculate other stuff first. So first I'm going to do a circular orbit with a period of 3.2 hours. Of course, there are 3,600 seconds in an hour, so I need to put 3.2 times 3,600 seconds per hour, and here is the answer to part A. The answer to part A is the inner orbit velocity is 6,013 meters per second. But what I need to keep track of is that the radius is 11,024 kilometers. Okay, so I needed those two pieces of information. Now I'm going to run my circular orbit program again, and this time put in an orbit period of 4.8 hours times 3,600 seconds per hour. Beep, beep, beep. And so the answer to part B is my orbital velocity is 5,253 meters per second, while my orbital radius is 14,446 kilometers, a number I will need to go forward from here. Okay, and by the way, if your answer is off in the last digit, that's insignificant. So if you said it's 8,067 or 9 kilometers, out there in the fourth digit and beyond is not significant. I'm now going to do the Hoffman transfer and put in the two radii. So I always have to put in the inner radius first, because my program will crash if I go backwards. 11,024 kilometers. I have to put in the apoapsis radius second, 14,446 kilometers. And now here's all the wonderful answers to the rest of problem 4. For part C, the transfer orbit's average velocity is not being shown yet. Next page. The semi-major axis was 12,735 kilometers. The average velocity is 5,594 meters per second. The periapsis velocity is 6,404 meters per second. The apoapsis velocity is 4,887 meters per second. Delta V1 was 391 meters per second. I have to write all this stuff down. Delta V2 is 366 meters per second. The total delta V, part H, is 757 meters per second, and the time of flight is 7,151 seconds. So there are the answers to problem 4.